Thank you. It's a daunting task to take over for Michael Schlesinger, not just because I don't have the amount of hair anymore to really pull this off, but it's also a daunting task because he had a very nice presentation. So he's unfortunately unable to come for a number of reasons which are very serious, so we hope he's doing fine. What I thought would be helpful then to have as the first talk a very, very broad and rough introduction about one potential way to look at the problem from the beginning to the end and to put everybody on the same page. And this was to some degree spurred by the dinner discussion yesterday at a table where we had oceanographers and psychologists at the same table, and then somebody said, well, what is overturning? And they're all very smart people, but sometimes the vocabulary just doesn't really jive. So I thought it would be interesting to have a talk where you show that you know maybe a little bit about a broad area without going deep. And so sometimes I might be missing a few because I'm talking already slang, but 80% of the people will be potentially bored because they knew that. And so the interesting point here is to put it together. There will be much more relevant talks about going deep later on. So here the charge is to see what are questions. And I think it always is potentially nice to start with real observations or with objective data. And what you see here is one approximation for temperature in central Greenland, which shows over the last 25,000 years, in some conversion from actually isotope concentrations to temperature, that when we came out of the last glacial into the interglacial we are right now, that compared to current rate in terms of temperature where the variance is relatively small, there has been a period where climate change, as measured here for temperature, has been abrupt. This poses questions of how do you define abrupt? What might cause this abrupt climate change? And is this abrupt climate change associated with crossing something that is referred to as a climate threshold? What is a climate threshold? How would we see it? How can we define it in a general sense? Where are those thresholds located in climate space? Not in the cold area where we're unlikely to return for the intermediate policy relevant future, but in the warmer climate here, which we have not spent much time, at least where we don't have very good records. The interesting point then comes up as if, and here I have to apologize, I spend way too much time now watching TV with my little one. Is it like Wile E. Coyote who sees the anvil dropping down, and when he looks up the anvil is here? So would we have enough time to see it coming? So is there confident detection or confident prediction possible? Or is this a situation where confident detection and prediction is an issue, is a nice goal, but something that might be very, very difficult to achieve? And also, and here comes the link to the social science, what are sound policies in the face of deeply uncertain climate thresholds? How are decisions being made? What are decision-making criteria that are applied? Which one makes sense? Which one are applied but don't make sense because the fundamental assumptions underlying those decision-making criteria are, this specific decision-making criterion are just violated. So those are a few of guiding questions that we hopefully get a little bit closer to addressing, or at least defining some more specific questions that help us achieving some solution. So there's the first question, what is the climate threshold? This is something that is defined in many, many different ways. Here is a picture from actually a class, rocks for poets or rocks for jocks, on a very simple way. One way to think about this is that if there's a system like the climate system, which has some stable basin of attraction, that if you perturb the system and you take the forcing away, there's a negative feedback which acts to restore the system towards the stable equilibrium. If you push a little bit here, for example, with climate forcing, it comes back, and if there's friction in the system, the return is slow and it's potentially slower than the forcing, and also it returns to the same state. In contrast, once you push it to a second state, which is an unstable equilibrium state, and you start pushing, you have a positive feedback which starts to act on the system, where the further you go, the steeper it gets, the more force is applied by gravity towards the ball, and a very small and smooth forcing can result in very fast and potentially irreversible change, at least irreversible over relevant timescales. So one way to define the climate threshold would be that a negative feedback switches to a positive feedback loop, that there are potentially several basins of attraction. In this case, there are at least two, namely here and here, and changes can occur abruptly. And the challenges that one can already see here are, there are several challenges, but one challenge is that a system where we have experienced for a long time around in stable equilibrium state here, and we have models which are finely attuned to represent this state here, those models might not work very well around here. And sensitivities that you have here might not work around here. But also it's a question of detection time. If you detect a change while you're here and you take the forcing away, you return safely to your original state. If you detect and forcing in a change while you have passed the threshold, like the French say, la carotte sont cuite, the carrots are cooked. You can only make carrots with cooked carrots with once you have cooked them, which means you can't really go back. And so here comes, this is a challenge of detection and prediction, but also a challenge of decision making. So this was very general. So what are potential climate thresholds in our system? Well, for that I would like to have two examples which have been analyzed numerous times. Those are examples that have been discussed at great detail in the NRC report on abrupt climate change. The program in this meeting is designed to some extent to widen this list to include more than just changes in the MOC and changes in ice sheets, and to have something about modes of climate variability. But so far, not most of it, but one of the prominently discussed climate thresholds is a potential collapse or threshold response of the North Atlantic meridional overturning circulation. I'm very sure that this will be discussed in great detail in the later sessions. So here I would like just to define a few words. There's an overturning or conveyor belt, refers to the question yesterday at the table, which refers to the overturning of water in an average sense in a roughly north-south direction. And you can make many arguments, but one that is important is that there are conceivable positive feedback mechanisms that could act to have the system react in a fast, abrupt threshold response. We'll leave it there, and where those feedbacks are, whether those feedbacks would be triggered, where they would be triggered, is a question that is so far deeply uncertain, which is one of the challenges in this decision problem. The second example is a potential disintegration of the Western Arctic ice sheet, which has been rising in the last 3 to 4 years in the dominance it has gained in the discussion of climate change and climate thresholds. One reason might be that based on literature reviews and some observations, it might be triggered earlier actually than a collapse of the meridional overturning circulation. But that's a very deeply uncertain question. What you have here is a very interesting example of a positive feedback, and one which you can actually say, because on the Southern Hemisphere and Arctic ice sheet is an ice sheet that is on land, and it is pinned to some degree, resists by slipping into the ocean by friction, that if you have a slip rate that would increase, the amount of friction would deliver heat, which increases the bottom temperature, which increases the temperature, and if you then have the ice being converted to water, you melt and you have more slippery, and hence the slip rate increases, and you have this potential for a positive feedback, which once it's triggered, it would go for a long time and become faster. And we have talks about ice sheets actually in this session, which will be much more detailed about this. The point that it's interesting here, and where this becomes, I think, interesting from a policy point of view, is that in the United Nations Framework Convention on Climate Change, there's this famous, some would say infamous statement about the avoidance of dangerous anthropogenic interference with the climate system, which is of course open to tremendous debate. And some have defined this dangerous anthropogenic interference with the climate system as crossing a climate threshold that would have distinct and widespread forcing. And so the examples of a collapse of the meridional overturning circulation, or persistence weakening, or a potential collapse of the West Atlantic ice sheet have been used as a poster child. And so if you follow this discussion, then the definitions of abrupt climate change, which is arbitrarily here defined as the response being faster as the forcing, the definition of hysteresis, when the system does not return to the original location after the forcing is removed over a relevant time period. This is actually a rather unscientific weasel word, and I apologize for this. Or a climate threshold, which is the combination either abrupt climate change or hysteresis response. And you see that if you want to have a physical distinct meaning to something like dangerous anthropogenic interference with the climate system, which is discussed in the UN Framework Convention, then you have to make many subjective assumptions, interpretations. What are the main points? Why is this a challenge for why is this a challenge in decision making? Well, there are many challenges. One, there are fundamental scientific uncertainties. But the other challenge, I think, is that the second one that comes to my mind here is that this is a situation where we face deep uncertainty. And I will have two examples why we think it's deeply uncertain. And deeply uncertain refers to the situation when you cannot define a clearly defined and reproducible probability density function of the relevant parameters, when the subjective priors become the main drivers of your predictions. And so point number two, decisions to manage climate thresholds have to be made under deep uncertainty, which also spans an interesting field-led or area of research where you have to think about what is the development of uncertainty, how do you characterize uncertainty, and how do you make decisions under uncertainty. So for the two examples here, this is a figure which has been potentially overused, and there will be certainly a new figure in the newest IPCC. This is from the last Intergovernmental Panel on Climate Change report, a comparison of models that of the meridional overturning circulation normalized to make it simpler to compare them, even though they have different background intensities, let's put it this way. And you see that if you force the model with some hindcast from 1850 to 2000, and then with a scenario, broadly speaking, there are models which are insensitive, where the MRC does not respond, and there are situations where the MRC is sensitive. There are, at least in this figure, and I'm sure Peter will give us a very detailed update. I hope so, maybe. Okay. Potentially, somebody will give us a detailed update on this. Doing this on the fly. Okay, there are peer-reviewed publications where the MRC collapses within this century. Whether those are the best models that are out there, whether those are the most reliable in terms of reproducing observations is another question. But you have a time window when there's a potential for a collapse in this century. On the other hand, there are a number of papers on the question of when we would detect changes. And the one benchmark paper by Ben Santer, who unfortunately couldn't come, says we wouldn't detect within the century, and most likely not within 2 centuries. Since then, we have had a few other issues, and you have to also define detection. Peter.
Okay, I'd like to make a point on this, but it's in fact misleading, I think, to do the deviation.
This is what I pointed.
Because you don't know what the mean value is. A reduction of 15 when your mean value is 45 isn't a collapse.
Yes.
So much more sensible.
It would be a relative reduction or reduction compared to the threshold in the model.
Much more relevant figure should be the percentage reduction.
Yes. Yes, I 100% agree with that. The main point I would like to, this is, This is not my figure, and one could argue the wisdom of the graphic design, and certainly Tuff would have different opinions about this. The point I want to make with this figure is just one simple point. There are many models out there. Right now, it is very difficult. I don't want to say possible or impossible, to say which one is more realistic. And this means that there is a wide uncertainty about potential collapse or not, and there's a potential for a situation where you would detect after you've forced the threshold. Whether this is a robust finding, we will find out later on. We'll see.
Excuse me, did you say you detect only after you have crossed the threshold? Is that what you said?
Yes. And this, of course, depends, and we'll talk more about this in the session on detection. It depends on what your detection threshold is, what your framework is, what your priors are, what your model structure, and so on how to design your observation system. Suffice it to say, you don't have to read through this wordy slide, that for the Western ice sheet, the situation is equally to potentially even more uncertain. And it has been, let's put it this way, the numerical models that are used for the Western ice sheet are great work, but they are missing important feedback factors, and so the predictions have to be taken with a grain of salt. The paleo record is very uncertain, and the literature is heavily divided on the interpretation of certain coral high stands on certain islands, and that's something which is right now very difficult to interpret. And so right now the level of risk as a function of temperature when you, for the Western Arctic ice sheet collapse, is subjective, and right now the risk estimates are done by expert elicitation. So this gives you one reason, and as soon as you get into expert elicitation, then you are into the realm of psychology, and we have interesting discussions about this by David Badescu and others. Okay, what are research questions? Well, I defined a few research questions at the beginning, but those are very general in a scoping point. I'd like to show a few toy resultlets that might point to a few questions or points where you can actually sink your teeth in and say, this is something which one could actually do in a reasonable time frame. For one is, if you use a typical economic model, this is a depiction of the economic model by Bill Nordhaus, DICE, which has an economic optimal growth model here, and then a gigantic environmental feedback. And you use this model to find a policy that optimizes the expected utility of the subjects. And so you start by assume an infinitely lived individual over many generations, which maximizes expected utility discounted at a social time discount rate. So there are already many assumptions. One is about discounting, one is about the specific way decisions are being made, namely that you weigh each outcome just by the probability without any other weighting in there. There's a utility which is concerned, and that you do know the probabilities of each outcome.
So you assume that there's a link between that it's only climate impacts which is causing economic damages?
No, those are economic damages due to climate change.
I mean, isn't it the perception of climate impacts which is doing the economic damages? That means there's a significant process between these two things.
Yes. This is a simplified picture, and I'm trying to make. Let me try to make one point with the next slide, and we'll come back to it. And I think it's the question of what is the perception, what is adaptation, and how does perception affect adaptation versus mitigation, which is, I think, one way you're leading towards is an interesting question.
I think it's a discounted damage in economic terms.
You don't have to, but here it is at the social rate of time preference. What we're getting into details. What I'm trying to do here is one simple example, which is this figure here. So you use this. Okay, let's start this over. Before Kyoto was negotiated, you picked up the New York Times. On page 1 of the New York Times, you found an article that says an economist at Yale University has analyzed the Kyoto Agreement and finds that it is economically inefficient. I'm paraphrasing here, and I could get the precise citation. And this has been derived with a model like this. So the question is, what do you get with this kind of model when you stick in those climate thresholds? And what you get is, if you have no control, what you see here is the carbon emissions that are allowable or that are there to give you a certain objective. If you have no control, so if we do business as usual, when you have a limit to stay with CO2 beyond a certain PCO2 level that would stabilize the MOC in a very simple model by Stocker and Schmitter in 1997, which means that you have basically to reduce considerably, and at the next 100, in this decade, end of this decade, you have to start decreasing emissions dramatically. If you adopt an Western Arctic ice sheet limit of 2.5 degrees, you have to stay flat, and then you have to decarbonize the economy rather drastically. And if you want to avoid an 1.5 degree limit, which some people argue would be harmful for corals and would cause widespread coral bleaching, you would have to decarbonize the economy on a rather drastic way. This is what those economic models give you once you stick in those very simple representation of scientific findings.
You're showing what the optimal policy would be, assuming various ingredients here.
Yes. So you stick in, you stay below 2.5 degrees C, you stay below 700 ppm C, and this is a cartoon. This is a straw man, and I'm trying to put fire to the straw man. Note that I'm published this so I can put fire to the straw man.
The other point I wanted to make is, although the optimal policies may differ by large amounts, the associated losses or values may not.
This is a point we'll get there, yes. So the damages and the costs are in the few percents to less than 1% of GDP. We'll get there. The point here is the following. One, I think when I drove here from the airport, the cab driver said, "Oh my God, we're really heating the planet and we have to do something," while he was driving his big SUV. So that's an observation which poses questions to me whether a rapid decarbonization to avoid 1.5 degrees C is feasible, or whether we have committed ourselves already, given the inertia in the system, to cross a few climate thresholds, like 1.5 degrees C. And that means we have clear feasibility constraints. A few options have been taken away by past action, by procrastination, because the economic model would have said in 1960s you should have done something, 1970s should have done something. In reality, we have done basically nothing. This is not a value judgment, this is a pure description of what has happened. The second point is that if we continue to do nothing and follow the red line, it becomes tougher and tougher to go down and stay within the constraint of those climate limits, which means if procrastination comes in, that one implication would be regrets either in terms of monetary damage, monetary costs, because you have to compensate with higher abatement for what you haven't done. It becomes even more expensive because of some economic nonlinearities. The details are given in this paper. But second, you might have regrets because you have closed the option to really stay below the threshold. And the most important point, this is where actually the interesting science comes in, from my point of view, is what is the effect of uncertainty? Note, this is a single line for a single best guess parameter. And if you just add in, so this is a best policy for the median case. This would fail in 50% of cases approximately to achieve the objective. In a former life, I worked as an engineer. If I design a drainage ditch which would have failed in 50% of all cases, I would have lost my job in a very short time. And so it becomes not an engineering question, but it becomes a decision-making question, whether there are certain reliability, certain robustness criteria which are potentially imposed if you want to make sound decisions which are consistent between how we invest into large-scale infrastructure, like dams, roads, and large-scale infrastructure decisions such as the climate system. Okay, which brings us to the point that there are other decision-making frameworks like 2 expected utility, and we could argue that the decision-making framework adopted here, which is still the decision-making framework adopted in most economic analysis, namely expected utility maximization, is violated because the underlying assumption that you do know the probabilities of each outcome are violated. And so we will talk in the third session. Robert Lampert will give a talk about what are alternatives to this. Is there something like reliability, like robustness, and a slide similar to this will come up. And finally, I think we come back to the science and to the natural science again, which has to do with the way science is done, science is reported, and the psychology of confidence or overconfidence. And I pick here just one example person, and we actually, without picking on somebody, this is an example. So this is an example that actually claims to make a probabilistic forecast of the MOC, and of course here it is actually in percent reduction. Although this graphing hides a few other issues which we won't talk about. And here's the mean, and here are some confidence limits. And so you could say that the insensitive model before, you can exclude at some type 1 error probability because you're out of the bound of here. It is well known that predictions based on a single model, when you include parametric uncertainty, are overconfident because you shortchange structural uncertainty. There are many examples of this. One is, a famous example is oil price predictions by the Energy Modeling Forum, which is a paper in Draper, in a very famous paper where he compares the oil price predictions of 10 or 14 Energy Modeling Forum models and the reality. Reality was out of the range. And so, yes, reality is very often out of the range of models that are there. And so the point here is that predictions like this run the danger of being overconfident. This also means that if you make decisions based on forecasts like this without accounting for it, we might have a bias towards too tight PDFs and too over conclusions. And if you want to exclude something at the extremes, which is where the damages become large, then overconfident model predictions are potentially a recipe for us not seeing the surprise and us being surprised. So
in this case, you see that the time after the publication date is obviously has a different statistical property than the time before.
yes, and we can.
Sure, it cannot be. So what does it mean then?
It's easy to predict the past, you can't predict the future.
Yeah, but I mean, that's one thing. But I mean, you see also the spectrum looks different.
Yes.
I mean, it's smooth curve before, but it's not smooth.
And we'll talk about this. But
there is another point, which had there been no change, they wouldn't have published it.
That's true. Yeah. A number of social aspects.
Yes. Okay, and so with that, I think I might have achieved my goal of boring 80% of you all the time and potentially having some discussions, but this was meant more as a warm-up of what are potential things and questions we could sink our teeth in. So what I would like to conclude is that, yes, abrupt climate change is potentially relevant for the policy point of view because it has been interpreted as one example of dangerous anthropogenic interference with the climate system. And this is a subjective statement, but second, those strategies have to be made under deep uncertainty. And third, there are many important issues which are overconfidence, alternative decision criterion, predictions that are too tight, detection time, prediction time that would benefit from a more detailed discussion. This is what, from my point of view, we're here for the next week. So, thank you. Any questions? Yes?
Maybe we should add something to the quality of the issue of abrupt change. I have the impression that it's to some extent rewarding to detect it. One is, it is, I mean, as you just pointed out, it is, so to speak, the, no. It is, so to speak, the ultimate essence of dangerous inference with the climate system.
Interference,
yeah. So it is the ultimate result needed to really push policy which is perceived as good.
Yes, for some people. Yeah, I wouldn't sign it or say this as an assessment of my way of doing science, but yeah.
Very fond of Keller, but in Europe, for instance, you're supposed to be, and so therefore I would take the liberty to say that. The second point is, of course, it is academically interesting.
It's a tough question, yes.
No, I mean, abrupt climate change is academically interesting. It's also tough, but nevertheless, I mean, it's rewarded. It's rewarded so ethically in the political realm, and it's rewarded academically, and one has to keep that in mind. This introduces certain bias into the process of climate science.
Yes, there are certain publication biases that are clear and obvious, and so if somebody...
That's a property of the issue of abrupt climate change, we should not forget.
It's going to be a lot of talk about models during this meeting, as you can see. If we just back off and talk about the economic component, are we going to talk about abrupt economic change, independent of abrupt climate change?
We will talk about the way how abrupt changes are represented in models.
Well, I'm trying to simplify it because we know about certain kinds of abrupt economic change that I believe was not forecast, like the collapse of the Soviet Union, the reunification of Germany. These are largely independent of climate change as far as we know. And so if you start to couple a model, now I don't know whether the Nordhaus model is capable of showing transitions.
Smooth line.
Is it known that it's known there are no transitions in the economics model? So does it make sense to ignore the possibility of abrupt economic change internal to the economic and political community in the presence of conceivable abrupt climate change?
I think you're putting your finger at a very interesting and important point that my philosophy of the model, or some philosophy of the model, is you have to have the same degree of being, oh my god, we can't do this when you look at a certain model. So you have to have, and you can't really have very sophisticated abrupt change in the natural science model. In the social science model, you have smoothness all over the place. That's the point?
No, well, I guess my point is we know that you do get abrupt economic change. And if the models are not displaying that, would one willingly then couple it to a yet more, not more, equally complicated model, and then in some sense claim that this must have skill? Or to put the question another way, does the Nordhaus model have skill, and do we know what it is?
Skill in terms of
well, forecast. I mean,
forecast.
If you took it back to 1960 and tried to do what meteorologists try to do, reforecast the next 20 years, would it do any better than what?
An earlier version of it that we did, that Bill and I did together for the '82 Academy report, generated probabilistic energy consumption in an aggregate level.
So this was 82.
Yeah.
So you could go back. I was reading this paper.
Yeah, and what we could do was either backcast or sort of start it earlier. And when we started it earlier, we started in '75. The interquartile range would pick up the implications on energy prices as well as economic activity of both of the OPEC oil shocks. So it was at least catching that. Part of the question that you're asking about sort of abrupt economic change is that economic systems do have enormous feedbacks in them that are self-correcting. So if you're looking at long-term growth models over 100 or 150 years, a 15-year collapse of the Soviet Union and recovery is probably...
Same is true of climate models.
that might be.
What is abrupt?
But the last point, though, I think is that climate policy can create abrupt economic effects. And I think that becomes a significant way of thinking about why to undertake near-term policy, and in a way where there may be all of these reward mechanisms out there for people to find thresholds of abrupt change and things like that, until somebody says that they're totally impossible. Then what you need to do is begin to think about what sort of adjustments might be required sometime in the future should those abrupt changes actually become robust findings and something that we're really quite concerned
I
about.
think that's not the question.
One response to him very quick and then to you. There have been a few publicity forecasts that really Python wrote a PhD thesis in '94 using a data assimilation with a lot of shortcuts, but interesting work where there are formal publicity bounds on predictions now roughly 11 years. So one could actually go back and look at this.
So nobody's done it.
No, not to my knowledge.
I wanted to reinforce this point because this is something I want to raise in my talk, but I realize that's at the end of the meeting, so I think it's a topic
Just make it now.
good for us. No, it'd be good for us to discuss. Not that I have that much to say about it, but simply I want to reiterate that it's a very important point. No one is discussing economic uncertainty, and I think if you believe some of the wilder predictions and possibilities, not just coming from climate scientists, but also from ecologists or people worried about water or depletion of oil or whatever you want to say. We can point out that the scale in which we're using the world's resources is unprecedented. And so why the devil should we think that we can go on predicting things that they're going to go on the way they always have? But I would say you can do it because that's what people do, but that doesn't mean that it's going to be a sensible way to proceed. Therefore, we should be considering the possibility of sharp, strong economic perturbations or change.
Which is precise. When you look at the special report on emission scenarios, they have very carefully sidestepped most of the time not to assign any probabilities to their scenarios, which is precisely the point. We cannot really. So if you say we need probabilistic forecast about the natural system, about the physical system, you also would like to have probabilistic forecast, which is arguably tougher, about the social system in order to make. But the other point is for those decision analysis, which assume you know the probabilities, once you start thinking about what we actually know about the probabilities, it becomes iffier and iffier, and you have to think harder of whether this is the appropriate decision-making criteria.
Sorry, there's one thing I forgot to mention. You're carrying out these analyses as if you know how to discount. But if you have economic uncertainty, it turns out the standard discounting arguments totally collapse. You don't get exponential discounting anymore. Sorry, folks, it's gone.
We can talk about Weizmann discounting hyperbolic in more detail later.
But my point is that it's relevant.
Yes.
And there's, as far as I don't see any place to discuss it on the
agenda. But we should talk about this when we can actually have an introduction about how discounting works, what are implications of the uncertainty, because otherwise we lose a large fraction of the audience. And I think we should do this carefully. What I was trying to do here is to have an outline of what's the scope, what we might want to talk about in a very broad sense. Okay. Yes?
If that THC picture of Reta Nutties is an underestimate of uncertainty, then is there any point running a model at all? Because there's not much left, is there? There isn't really those bounds.
Oh, well, the bounds could be, here. No, you're the expert. Come on. Well, I think there's a point. I think there's a point in drawing consistent, reproducible conclusions from a set of assumptions which are reproducible and which gives you an idea about the spread of potential outcomes. And this is, from my point of view, why we do realistic analysis. And so I think an overconfident prediction from a decision-making point might actually be worse than saying we cannot make a prediction at all.
Models need not be sufficiently realistic that the bounds are underestimates. I mean, an analogy would be, if I'm trying to understand how a 747 is flying, and I use a model made for a DC-3, I can make a very nice prediction, I can make a very nice ensemble, but of course it's garbage.
Yes.
Because the thresholds for a DC-3 stall and so
are very different.
Are completely different. And whether it's more unstable or less stable, I actually don't know, but it could be either way. And to assert that whether the bounds are too wide or too narrow seems to me is a very deep question.
Yes, but we agree that knowing the mechanism gives you is a potential for a better quality forecast.
Okay, but is this a DC-3 climate or is this a 747?
That's an EMIC. That's an EMIC 2.5. So it's an EMIC climate. So I'll let you. And so I'm a I'm a glider pilot. This is actually, this is, free, gliding climate.
A glider.
This is a glider. No.
We're on the 747.
Well, but the physics, okay, without sounding trite, the physics of flight is the same, and maybe some conclusions can be drawn, and some conclusions you can do with EMX. Yeah, we'll get into this.
If you say that's too...
It's not a sharp forecast.
You said there's nothing. If it could go up or it could completely collapse because that is too...
Well, but what's the median? There is information here. Well, we'll talk. Well, okay. I'm glad we initiated this discussion. We will have lunch in a few minutes. Holy smokes, tough crowd. No. Let's. We can sort of discuss this. It's a challenge.
Is it unimodal?
It depends on what you call a prediction. Let's first find the word and then find out if it's enough.
But the other point is, what does a decision maker need? If you go back to economic models which only care about a fig line here, you don't care about the bounds. If you think about a risk management strategy which has actually some reliability or robustness criteria involved, then you do care deeply about this, and you care also about the accuracy of the width of the confidence.
Is it even unimodal?
Plus the problem is that the so-called decision maker has not only this diagram, he has about approximately 1,000 of these diagrams. And so it's only one. I mean, and the other one has something to do with unemployment, and then with unexpected new diseases, and things of that sort. And then it really becomes difficult to predict a decision. I mean, if we only have that diagram. So if climate would be our only concern, then maybe policy would be much easier, but I have the impression there are more problems in the world.
Yes, of course. And, then you get into the Copenhagen consensus or lack thereof arguments, which we won't hopefully not get into this meeting. Yes, but then you want to be at least somewhat consistent in your trade-offs. You don't want to have value of life saved.
Imaginary policy decision maker. Yes. Then we should have not the model of a decision maker which has to take one decision, but he or she has actually many.
I'm glad you raised this point, and one point in the slide when we talk about in the second session is how do decision makers make decisions, and this means we have to talk to them. We have to analyze this in a somewhat scientific way, and I'm glad. I'm sorry to always point to you, David. we have experts on this, and there are actually people who do this for a living to analyze decision making, how people do that. We have to think about this, but it's also an issue because typically natural scientists don't go there for many reasons. Questions? Lunch. I'm ready for lunch. Wow, already. Thank you. This is going to be a tough week. Oh my God! Never.